This talk is about the complexity of a variant of multi-prover interactive proofs involving entangled provers. This is a joint work with Seyed Sajjad Nezhadi and Harry Yuen at the University of Toronto. Our result is an equality between two complexity classes. We show that the complexity class MIP star, zero gap, is the same as the computability class pi2, belonging to the second level of the arithmetical hierarchy. I will define all these complexity classes precisely in a few slides, but for now let me begin by breaking down the notations in this equation. MIP here stands for Multi-Prover Interactive Protocols. A star denotes that the provers in this protocol can share quantum entanglement, but as is the case with classical MIP, the provers are not allowed to communicate once the protocol begins. Zero here indicates that this class allows for zero soundness completeness gap. On the other side of the equality, we have pi2 from computability theory. Pi2 belongs to an infinite hierarchy of classes known as arithmetical hierarchy. 2 here refers to the level of the hierarchy, and to get a sense for how large this class is, I'll point out for now that it strictly contains the class of recursively enumerable languages, and the latter contains the well-known halting problem. Another way to state our result is in terms of non-local games, which we will define precisely in a moment. Our result, phrased in this way, states that computing the value of an entangled non-local game is strictly harder than solving the halting problem. Slavstra had previously shown that this task, computing the value of an entangled game, is undecidable, but the precise characterization of the hardness of this task was not known. And we have here one last notation to introduce. The number of provers allowed in an MIP star protocol is denoted in the bracket. Our result states that pi2 is in fact contained in MIP star 0 with 3 or more players. Here I would like to note that reducing the number of players to 2 refutes the Kahn's embedding problem from the theory of von Neumann algebras. We know that the Kahn's embedding problem is false from the recent MIP star equals RE breakthrough result. But this relation to Kahn's embedding shows that reducing the number of players in our work is perhaps a very difficult task. So the different flavors of multi-prover interactive proofs fit very nicely in a diagram. Dating back to 90s, we have the celebrated result that states that MIP is equal to NX, the non-deterministic exponential time class. The recent breakthrough result from earlier this year proved that MIP with entangled players is the same as the set of recursively enumerable languages. Our work, in a sense, completes this picture by characterizing the zero-gap variant of MIP star in terms of other well-known complexity classes. So we are now going to define the main objects in our result. Let's start with non-local games. A non-local game can be thought of as a multi-prover interactive protocol with one round. More precisely, a non-local game G is played between a verifier and multiple entangled cooperating provers who cannot communicate with each other once the game starts. The verifier first samples questions for the provers, and the provers attempt to respond according to a quantum entangled strategy, S. And they try to do so by maximizing their winning probability. The probability of winning a game G with a strategy S is denoted by omega star of G and S. The maximum winning probability of a game G, also referred to as value of the game, is denoted omega star of G and is defined to be the supremum over all strategies of omega star of G and S. MIP star K is the set of languages L for which there exists a K-prover family of games Gx, one for each string x, such that two conditions are satisfied. The completeness condition states that if x is in the language, then the value of the associated game Gx must be 1, and the soundness condition states that if x is not in the language, then the value of the game Gx must be less than half. Then MIP star is going to be the union over MIP star K for all K. The zero gap variant of MIP star is exactly the same, except that the soundness requirement is relaxed. So here, soundness requires that if x is not in the language, then value of the game must be less than 1. But this value could be arbitrarily close to 1. Because of this relaxed soundness, this class is perhaps larger than MIP star. Our work proves that this is indeed the case, that MIP star 0 contains more languages than MIP star. Also, MIP star 0 has a very natural complete problem. The problem of deciding if a non-local game G has a perfect strategy is complete for this class. Arithmetical hierarchy is an infinite family of classes. At the bottom, we have the well-known classes RE, co-RE, as well as their intersection, which is the set of decidable languages. In this diagram, arrows indicate containment. And one thing we know about the arithmetical hierarchy is that all classes are provably distinct. So the class that concerns our work, pi2, sits in the second level and is strictly larger than the union of RE and co-RE. Let's recall the set of recursively enumerable languages. A language L is recursively enumerable if there exists a Turing machine M such that X is in L if and only if M accepts with when X is written on the input tape. The well-known halting problem is an example of a complete problem for this class. There is a second characterization for classes in arithmetical hierarchy that uses alternating quantifiers and decidable predicates. In this characterization, L is an RA language if there exists a decidable predicate P such that X is in the language if and only if there exists an N such that P evaluated on X and N is true. Here, by a decidable predicate, we just mean that there is an algorithm that evaluates P on every possible input pair. Pi2 is defined similarly. A language is in Pi2 if there exists a Turing machine M with oracle access to the halting problem, such that X is in L if and only if M accepts X. And similarly, in terms of quantifiers, L is in Pi2 if there exists a decidable predicate P such that X is in the language if and only if for all N there exists M such that P evaluated on X and an M is true. So our goal is to show that MIP star equals pi2, showing that MIP star 0 equals pi2, and showing that MIP star is contained in pi2, one side of this containment, is in fact straightforward. Recall that a complete problem for MIP star is to decide, given a game G, whether it has a perfect strategy. But this can be phrased as a pi2 formula with a for all and an existential quantifier. More precisely, a game G has a perfect strategy if and only if, for all epsilon, there exists a strategy S such that the value of the strategy is at least 1 minus epsilon. Given an epsilon and a strategy S, deciding whether the value of S is larger than 1 minus epsilon is a very simple task, and in particular it is decidable. This proves that MIP star 0 is contained in pi2. Now the other direction uses two very strong results. The first tool we use is known as protocol compression. It was invented and successfully applied in the Fitzsimmons et al. Paper from 2019 to show that core-E or pi1 is in MIP star 0. To improve this and show that pi2 is indeed in MIP star 0, we rely on another tool called the halting protocol, which is proved in the MIP star equals RE result by G et al. I'm going to explain both these protocols, and then I'm going to show how we can combine the two to get our result. The compression theorem, the first tool that we use, it takes as input a family of non-local games, G, and efficiently produces a compressed family of games, G sharp, such that the values of the nth game in the two family are related with one another in a nice way. First, we want that the nth compressed game to always have a value that is larger than half plus half the value of the nth game. Secondly, we want that if the nth game has a value less than 1, then so does the nth compressed game. So what is it that being compressed? It is the runtime of the verifier in the nth game that is being compressed. Specifically, the compression theorem guarantees that the running time of the verifier in the nth compressed game is polylogarithmic in the running time of the nth game. So it is much faster, the compressed version. And let's use the compression theorem to prove that core-E is in MIP star 0. To do that, we just need to construct a game from any core-E formula such that the core-E formula is true if and only if the value of the game is 1. A general core-E formula states that for all n, a predicate P is true when evaluated at n. So this just follows from the quantified characterization of core-E. And on a Turing machine, to determine the truth value of this formula, we have to loop over all values of n. Using compression theorem, on the other hand, we can circumvent having to enumerate all n. So more precisely, if we construct a family of games Gn, one for every n, the nth game is very simple to describe. The verifier in the nth game first computes P of n, and it rejects immediately if Pn is false. However, if Pn is true, it plays the compressed game G sharp n plus 1 with the provers. Note that this is not a recursive description. The games G sharp are not the same as the games G. Intuitively, however, the compression theorem, because of the way it relates the values of G and G sharp, allows us to treat the two games as if they are the same, at least when it comes to the analysis. We show that the first game G1 in this family has the desired property, namely that it has a perfect strategy if and only if the query formula is true. So how do we prove that? Well, for the analysis, first consider the case when the query formula is false. For concreteness, suppose P evaluated at 3 is false. Then by construction of our family of games, the value of game G3 is 0. And by the guarantees of the compression theorem, we know that the value of the compressed game G3 is also less than 1. This step in our argument is illustrated by this green arrow that, from G3 to G sharp 3 in the diagram. Now, look at the description of G2. It first evaluates the predicate P at 2, but since this evaluates to true, the verifier then runs the compressed game G3. Thus, the value of G2 is the same as the value of compressed game G3. So the value of G2 is also less than 1. This step of the argument is indicated by the red arrow from G3 to G2 in the diagram. Repeating this argument a second time proves that the value of G1 is also less than 1. So to summarize, if the predicate is false, then G1 has a value less than 1. Now we have to prove that if the formula is true, then G1 has value 1. Well, first, look at the bottom of the diagram. From the construction, we know that value of G1 is the same as the value of the compressed game G2. From the guarantees of the compression theorem, on the other hand, we know value of the compressed G2 is at least half plus half the value of original game G2. So the value of the first game is at least half plus half the second game. Continuing this argument k times, we get that the value of the first game is at least the sum of the first k terms of a geometric series. So taking k to the limit, the geometric series approaches 1, and we get that the value of the first game is 1. So I explained the compression theorem. Now the last object we need is the halting game. A theorem of the result MIP star equals RE states that for every Turing machine M, there exists an efficiently computable nonlocal game GM such that if M halts, then the value of GM is 1, and if M loops forever, then the value of GM is at most half. So in a sense, this game decides the halting problem. Now, this halting game proves the result RE is contained in MIP star. Let's see why. Well, we saw query formulas. An RE formula, on the other hand, has an existential quantifier instead of a for-all quantifier. In order to show that RE is contained in MIP star, we just need to show that for every RE formula, there exists a game such that the formula is true if and only if the game has value 1. So take the RE formula, there exists n such that P evaluated at n is true. Now consider the Turing machine M that loops over n and halts if and only if P evaluated at n is ever true. So the machine M halts eventually if and only if the formula is true. Therefore, the corresponding halting game Gm has value 1 if and only if the RE formula is true. So this completes the proof of the containment RE in MIP star. Now, back to our result, we have to construct a game for a pi2 formula. In a pi2 formula, we have a for all quantifier followed by an existential quantifier. We first construct a game that eliminates the existential quantifier. The existential predicate, the inner predicate, is an RE predicate, so we can decide it using the halting game of the previous slide. Let's be a bit more formal. The pi2 predicate states that for all n there exists m such that p evaluated at n and m is true. For every n, we can construct a Turing machine Mn such that it halts if and only if p evaluated at n and m is true for some m. Now we can replace this Turing machine Mn with the halting game Gmn. So the pi2 formula is equivalent to saying that for all n, the value of the game Gmn is 1. So we eliminated the existential quantifier. The new formula that states that for all n, the value of Gmn is 1 looks like a query formula. So we can eliminate the for all quantifier using the exact same idea we used to prove that query is contained in MIPzero. We construct a family of games Gn, 1 for each n. The verifier in game Gn first invokes the halting game Gmn. If the game is lost, the verifier rejects immediately. Otherwise, it plays the compressed game G# n+1. Now we can argue as before that for all n, value of the nth halting game is 1 if and only if the game G1, the first game in the family we just constructed, has a perfect strategy. We will present two open problems. The first open problem asks whether pi2 is contained in multi-prover interactive proofs with 2 players. We said earlier that this would refute the Kahn's embedding problem, so we expect that this is a difficult task. And the second open problem asks for a characterization of another variant of the MIP proof systems. Informally, MIP is the same as MIP star, but now the provers can share infinite amount of entanglement. And this is the last variant of the multi-prover interactive proofs that is not fully characterized in terms of more well-known classes. We know that it is contained in query. We also know that it contains PS space, but where it sits exactly is not known. And with that, I would like to end my presentation, and thank you for your attention.